Hey everybody, and welcome to Module 3, Lecture 1 for ME14, Mechanics of Solids. So today in this module, what we're going to be doing is primarily focusing on a couple example problems. So we're going to be going through a lot of the material key equations and theory that we saw in Module 2 and applying to them some example problems, and I'm going to go through my hand solution to those. So as you saw in the overview video I posted up, typically I normally would break chapter 2 into 2 different weeks. So the first half of chapter 2 we would have done in module 2 with example problems, and the second half of chapter 2 we would have done in module 3 with example problems. But I was looking at the way that a lot of the example problems went, and the ones that I wanted to go through with you guys involved the material that was covered throughout the entire chapter. So what I chose to do, especially considering this is an online course, was just dedicate all of module 2 to just going through the theory and applications and key equations, and then within module 3 really start looking at some of these hand solutions and different problems and a few applications as well. So what we're going to do now is I have gone through and picked out a couple different example problems that I went through and solved by hand, and we're going to go through my hand solutions, talk about the formatting that I expect for homeworks and exam problems, and apply that format to these problems that I solved through. So the first problem I wanted to take a look at was right from the beginning of chapter 2. So this is problem 2.1. Now in this problem here, they don't give us an initial diagram. They just give us the word problem here. So we need to take and read through carefully with this word problem and maybe even develop our own diagram from what's described within this problem statement here. So in the problem statement, they tell us we have a 2.2 meter long, so we know our length, of a steel rod. So now we know the material and the shape of it as well. And this must not stretch more than, so they give us our deflection here, our delta number of 1.2 millimeters. So right off the bat, as I'm reading through this problem, there's a couple things I really want to pay attention to. First thing here is units. So they're telling me they're giving me the length in meters, but they're giving me my deflection over here, the elongation here, in millimeters. So I really want to pay attention to that and make sure when I start writing down and creating my setup page that I determine what units I want to use for this problem and do any of the conversions that I may need to do to keep everything in the right units. That being said, that leads into unit analysis. So that's another thing as we're going through and solving these problems out by hand, is we want to do out the unit analysis. Include these units, cancel out where we can to make sure that we stayed on track, we plugged in things correctly, and we have the appropriate units. So it's not to stretch more than 1.2 millimeters when subjected to, now they give us a tension force here of 8.5 kilonewtons. Again, pay attention to our units. It's not just newtons, it's kilonewtons here. So what are kilonewtons? How do those relate? And the fact that we're in kilonewtons rather than newtons. Now they also tell us that knowing that our modulus of elasticity, our E, is equal to 200 gigapascals. So again, we're in gigapascals, not pascals here. So pay attention to what that's going to mean as we plug that in as well. Now that's everything they've kind of given us in the problem statement. Now they're going to tell us what they want us to solve for. So they're asking us to determine, in part A, the smallest diameter of the rod that should be used. So we're looking for a diameter, we're looking for a length here, we got to think about what units we want to use for that, and we're looking for the smallest one right there. So this is just part A. Part B, they're asking us to now solve for the corresponding normal stress, or sigma value here in the rod. So again, if we're reading through this, we really want to organize this and create this setup page. It's a lot to go back through, defer, do our unit changes and analysis, and try to figure out what exactly they're asking for, what they've given us in this. So what we want to do is take this information from the problem statement, make a setup page, write out all of our givens. What do they give us in the problem, clearly labeled, and we're also going to have all the things that it asks to solve for clearly labeled. And in this case here, maybe we want to create our own diagram because they don't give us one in the problem statement. So that's exactly what I do here. I take that information from my problem statement, I create up my setup page. I have class on here. Normally you'd have your name up here in the top right if this were a homework assignment, what the due date was, what assignment it was right there. So you write all that information up here on your homework assignment before you scan it and submit it to Blackboard. So this right here is a chapter 2 example problem. So I've labeled what problem it is here. It's problem 2.1, and I want to take that information, what was given to me in that problem statement, read back through that carefully and write this out. And what you can notice here is there's 4 different things that I've written out within this problem statement right here within my givens. I have the variable name, I have the numerical value, I have the units I'm using, and I'm having how it physically relates to this problem here. So L is my rod length. It's given to me as 2.2 in units of meters. So that's the first thing. Now they gave me this elongation in the problem there, and they give it to me as 1.2 millimeters. I've realized I want to work in meters with everything else, so I've converted this to meters right here. So I say delta, my variable delta, which is my elongation in this case here, is 1.2 times negative third when I convert it to units of meters. So now this is all in one spot that I can reference back to as I go through and solve this problem out. So then I go to my tension force here, which I'm giving the variable name P, which is standard within this textbook and a lot of the other example problems we've seen. And I note this is now, if I convert from kilonewtons to newtons, this is in 8.5 times 10 to the third when I get out of kilonewtons and put it in newtons there. And then lastly, they've given me my modulus of elasticity here, or my E, which they gave us as 200 gigapascals. I want to convert this to pascals, which is also newtons per meter squared. So everything else is newtons and meters. Let's get it in that same units right there so we know we can cancel things out when we do our unit analysis and solve through this problem here. So it's now 200 times 10 to the ninth when I get that giga right there in units of newtons per meters squared or pascals. So now I have all my given information from the problem statement nice and neatly organized in one page that I can reference back to. What I've also done here is I've drawn out what they told me. They told me it was a steel rod. They told me the diameter down here is what we're looking for. It's got some diameter that I'm calling a variable D. It has my loads. You can see there's my loads right there related down to my load here. And here's my length of the rod right here related to my length right there. Now, one thing that you notice is that I draw out this diagram right here. I want to keep it as simple and neat as possible. So one thing I've done is I've only included the actual variables and not the actual numeric values associated with these. Start putting in the numeric values and your units within that there. It gets cluttered and disorganized very quickly, especially with more complicated diagrams and figures. So I just put the variable names up there, my P, D, L, right there. Those are the only things I'm really including in that right there. They can reference down what is P. I can go down to my givens. Oh, P is my tension force, and here's my value, and here's the units it's in. So it's all on one page. I can reference it. It keeps the diagram neat, organized, and separate. All my givens are down here in the right units, have the numerical values. So as I'm choosing my governing equations and I solve this problem out, I can quickly flip back to this first setup page and say, that's my length, that's my deflection, that's my load. Plug those values in when I'm ready. Now, the next thing I want to do is within that problem statement, I want to figure out what they're asking me to solve for. So within that, they're asking me two different things. Part A and Part B, I've clearly labeled those Part A and Part B down here. And now what I can see in Part A, they asked for the smallest rod diameter. So I'm looking for that diameter, relates back up here to my diagram. There's my diameter D right there. That should be used. So I called this here, I even label here. That's my diameter, my variable name D, related back to the diagram. Then in Part B, they've asked me to solve for our normal stress in the rod here, or my sigma value right there. So I clearly have this labeled for what variable I'm using for that. So now I've taken the time, read through that problem statement, understood what they've given me, clearly organized, written it down with the correct values, units, how it relates to my problem, and I clearly down below that have now what I'm asking me to solve for in the problem here related to which variable names. So now this is going to make my life so much easier when I go through, begin my solution, need to start plugging in to my governing equations. So moving forward, our next step is to begin our solutions, and the first step in that solution is to take a look and figure out what is our governing equation. Well, again, having that setup page and seeing this is what I have, this is what they're asking me to solve for, that helps me choose which of those governing equations. I can flip through my textbook, I can flip through the lecture slides from Module 2 and take a look and say, I'm involving load, modulus of elasticity, length, and deflection, and I'm looking for something related to area, which is diameter, so I can relate that to area. What equation, what governing equation can I use? I can go back to page 70 in my textbook and look at equation 2.9. I have this relationship here. My delta is equal to my load right there times the length of our rod divided by the area times our modulus of elasticity. Well, we have everything we need in this except for area that we can solve for, and within area is our diameter that we can solve for there. So what I do, I go back to my setup page. Here's my governing equation now written out here, where here's my known values. I got these directly from that setup page. I just flip back and look. So because I'm doing a slide right here, I can't necessarily have them both up next to each other. So what I've done is rewrite these out here. So for this governing equation, I know my load is 8.5 times 10 to the third newtons. I know my length of this is 2.2 meters. I know my modulus of elasticity is given to me as 200 times 10 to the ninth in newtons per meter squared, and my deflection is given to me as 1.2 times negative third meters, or 1.2 millimeters there, but I want everything in meters and newtons, so it's all going to cancel out. Unit analysis is going to be your best friend within these problems, especially as they get more complicated. So then I can take and do an intermediate step after this here and plug in these known values. So that's exactly what I do. Put my P in for my P value there, put my length in for my length right here, my modular elasticity value for modular elasticity there, and my delta for my delta. So what you can see I've done is I've rearranged this equation and solve for A, which contains my unknowns. So I do that down here, plug in my known values. And another thing that you can notice that I did down here, I included my units. And I wanted to do this so that I could do out my unit analysis. So I write this down here. My load is 8.5 times 10 to the third newtons times my 2.2 meters for my length. Down here I have on the denominator here my modular elasticity is 200 times 10 to the 9th in newtons per meter squared. And then I have over here my deflection of 1.2, or elongation of 1.2 times 10 to the negative third meters. I can look and say, meters and meters cancel right there. My newtons cancel with my newtons right there. So I'm left with 1 over meters squared, which would give me meters squared. And that's exactly what I would expect for area. So that's my double check right there. I have the right units that lets me know, hey, I'm on the right track. I used the right units. Everything cancels out. If I would have saw meters and millimeters here, I would have known I forgot to do a conversion. Or if it didn't come out to meters squared and there was an extra time constraint there, I realized I might have plugged in something wrong. So this lets me know I'm on the right track. I plug this into a calculator, Excel, MATLAB, Python, your choice. And I end up with calculating my area now of 77.917 times 10 to the negative 6 in units of meters squared. So now I have my area. Now this is something where it's easy to kind of get sidetracked along the way and say, great, done. I have area. Well, they didn't even ask me for area. Part A, they asked me for diameter. So now what I need to do is how do I relate area to diameter for this rod? So that'll be the next thing that we're going to do, is figuring out how to back our diameter out of this area. So what we recall is, we'll start with our very basic. When I choose governing equations, I like to choose the most basic general one, expand upon it, and then go from there. I know we can Google search or go through our textbook and find specific formulas for one specific thing, but understanding where those specific formulas come from and how we derive them is part of engineering. And it's a great process to have, because when you're out in a job or in grad school or wherever you go after this, there's going to be an instance where you need to come up with this governing equation. You may not have memorized every single specific one. Remember, yeah, I got to go back to Newton's law. Or, oh yeah, I need to go back to an area formula. You might know the general one, and you'll know how to derive it from there. Even though you didn't memorize a specific one for that specific problem you're working on, you know where it comes from and you know how to get there. So that's what I do here, is I start with this real general one. Area is equal to pi r squared. So I come down here, I say, well, I'm not looking for radius, I'm looking for a diameter. What's the relationship between radius and diameter? Well, diameter is equal to 2 times my radius. Great, but I want to solve this for radius, so radius is now equal to my diameter divided by 2. Well, in this formula up here, our radius is squared, so if I square my radius on the left side, I need to square my right side over here, so d over 2, this entire quantity squared there. So therefore, radius squared, when I distribute this through, is equal to d squared over 4. So now if radius squared is d squared over 4, I can plug that back up in here for my radius squared right there in my area function. And what I end up with is area is equal to pi times d squared over 4, which is now my general equation. Like I said, you could have looked this up. Maybe you had it memorized for how to do this for diameter rather than radius. But just as an example of starting with a general form of equation, everybody remembers pi r squared. You might not remember pi d squared over 4 off the tip of your tongue, or if we weren't dealing with a specific geometry, maybe something else, you might not have it memorized for diameter versus radius. Start with the most general one, take the time, expand it from there. So from there, what we can do now is we can figure out, okay, what I'm really interested in, they asked me to solve for here, was this diameter. So I can rearrange and solve this for d, so I start again, and I'm going to break this down and do it step by step. Just as an example, I know this is a really simple one, but I just want to do this as more of a showing you the concept of what I'm expecting to see for some of these more complicated equations starting from the general form. So I have here area is equal to, now this is my pi d squared over 4 right there that came from up above here. So all I've done is written this down here. Now if I take and multiply both sides here by 4, and this is something to note too, when you're solving out your homeworks, doesn't hurt to put these little notes on what you did. It allows you to go back and look at your work and understand how you got from one step to the other. It allows one of your teammates, co-workers, to go back, and if they're picking up a project that you were working on, to see what your thought process was. And in this particular case for this class, it allows the TA to know what your thought process was in solving this problem, and possibly award you partial credit in case you did plug in something wrong or drop a negative along the way. So we multiply both sides by 4. The 4 comes over here. We're now left with 4 times area is equal to pi d squared. Well, we want to get diameter by itself. So now what we want to do is divide both sides by that pi. We do that there. We move our pi over here. 4a over pi is equal to d squared. Next thing we want to do is take the square root of both sides there to get d on its own. So d is equal to the square root of 4a over pi right there. So this is our relationship now for our diameter right there. So now that I have this relationship so I can solve for diameter based upon my area right here, I can go ahead and plug in that area that I solved for previously. So I say over here where A, my area is equal to 77.917 times 10 to the negative 6 in units of meters squared. So I'm still in meters, which is good there. Plug this value in right there for that A term, and go ahead and solve it out. So 4 times my area value right there divided by pi. Plug that in, take the square root of it. Again, your choice. Do this on a calculator. Put this into MATLAB. Put this into Excel, Python, whatever your choice is. We do that there. We find out that diameter is equal to 9.9603 times 10 to the negative third. Units are still in meters. We took the square root of meters squared, which gives us meters. So that diameter should be in meters. That's our double check. Unit analysis, again, is going to be your best friend as you're going through, especially as these get more complicated. So this, if we go back to our setup page now in our problem, this was part A. So we're not done. We've done a lot already. We're already on page 5, page 6, whatever it is here. And we're saying, okay, great. Nope, we're not done yet. This is just part A. We can flip back to our setup page and say, yeah, there's a second part that they asked us to solve for on this problem. So that's where we're going to go from there, is to now go on to part B. So in part B of my problem, I've clearly labeled this up here. Start this thought process all over again for our solution. First thing we want to do, look what we're given, look what they're asking us to solve for, and come up with a governing equation. So in this case here, we can go to equation 2.3 on page 61 of our textbook here. And this tells us that sigma is equal to load over our cross-sectional area there, where we already have some of these values right here. We are given our load as P is equal to 8.5 times 10 to the third, and we convert it to newtons rather than kilonewtons right here. And we've already solved for our area in this case here. So area we've solved for as 77.917 times 10 to the negative 6 in units of meters squared. So we have units of newtons and meters squared right there. So because we've already solved for this in part A, we can simply plug our area back in right there, and we can plug our load right back in here for P, and it's a straightforward plug and chug at this point for this problem in part B. Nothing too complicated. We just had to find that correct governing equation based upon what we were looking for and what information we're given and already solved for. So we do that there. We plug in for our sigma. We take our top here. Our load is 8.5 times 10 to the third units of newtons. And on the bottom here, we have our area, which is 77.917 times 10 to the negative 6 units of meters squared. So we do that our math here, and what we find is this is 109.1 times 10 to the positive 6 in units of newtons per meter squared. Well, newtons per meter squared is pascals. That's what we should expect to see for our sigma value right here. Everything does double check, and that is part B for our solution to this problem. Let's take a look at another example problem from chapter 2 here. So this problem here we're going to look at is problem 219. So in this one here, they actually do give us an initial diagram, which is a little bit more information, which can be a positive and a negative. The positive side is we actually have a visual representation. We don't need to infer this from the entire word problem here. The downside of this is now we have 2 places to look for all the information to make sure we capture everything that they give us within this problem here, both in the word problem portion of it up top and everything that's drawn in on our diagram down below. So in this here, they tell us both portions, so this lets us know there's 2 different portions of this. Rod A, B, C, they're calling the whole thing, are made of aluminum. The entire thing is made of aluminum and has the same modulus elasticity for both the top and bottom portions. So that's great there. Now, knowing the magnitude of P, now what we need to do here, they just tell us P in the word problem, so we need to reference down to our diagram here to see what P is. And P is this load that's applied at the top portion of this here at A. Now, this is given to us as 4 kilonewtons. Pay attention to our units here. It's in kilonewtons, not newtons. Now, with that information, they ask us to solve for 2 different things now. First thing that they ask us to solve for in part A is the value for Q, so that the deflection of A is 0. So there's a lot of information given just within that one little portion right there. The value of Q. So we come down here, and at point B right here, we can see this load Q. So the first thing that we know is 1, Q is in a different location than point P up here. It's down here located at B. And also the direction is opposite. Our P is going up this direction, our Q is going down in this direction. So other thing that we can infer here is all the dimensions. The dimensions were not given in our problem statement. We can just physically see them down here in our diagram. So the length of AB is 0.4 in units of meters. Our length of BC is 0.5 in units of meters. And our diameter of BC is 60 millimeters. And our diameter of AB is 20 millimeters. So in part B, they're asking us to find the corresponding deflection of just point B, which is right at this point right here. So what I like to do with these problems is think about them in terms of a physical object. So if I can see that P is going up and I pull on the top of P right here, just as we know, we pull it with the set load of 4 kilonewtons here, I got to stop and think, what's physically going to happen? Well, if I'm pulling point A right here and I'm pulling up in this direction, and I can see down here at the bottom of member AB is going to be a force here pulling down at Q, what's going to happen to member AB? So thinking about this really helps you keep track of sign convention and what you're going to actually solve for. Is it compression? Is it tension? All those type of things. Is it going to shorten? Is it going to elongate? So one thing that I can take a look at this and pretty confidently say is, okay, if I pull up with P and I pull down with Q on this smaller member AB, the length is going to change and it's going to elongate. Now, if that elongates in those directions there, the next question is, well, if I'm looking at BC, what's going to happen to that? And as a side note, that's definitely something that we want to do with these problems. Break them down into individual sections and solve them and think about them separately. Think of AB and BC and what you're solving, what's happening with each of those separately, and then at the end, combine them as a whole, as a system. So as we do that there, we now think about BC and we say, okay, if I'm pushing down on BC and it's fixed rigidly down here on point C, what's going to happen to member BC? Well, likely what's going to happen to member BC right here is, depending on the values of P and Q, potentially member BC could be compressed. If we're pulling down on B right there, we're pulling up on A right there, well, likely this could go into compression as well, again, depending on the values that we see between P and Q right there. So then we think about what happens to diameters, what happens to their shape and length when it's something that's tension versus compression, and all of that there. Now, how does this tie into other courses you're going to see later on? So this is something that I do want to stop and mention for you. So I mentioned about solving for these piecewise, as individual components within a system. So it's hard to think of this as a two-part thing. It's pretty simple, but it still is individual components. You got the component up here, the member AB, and you got the component down there, the member BC, and the whole rod ABC as your system as a whole. So as you move on to courses, let's say like ME 171, your design of elements course there, this is where you're thinking about designing even more complicated problems like this with more parts, and you want to break them down and think of each component separately, each part separately within it, solve that for all the issues you need, run your testing analysis on each individual part. Then as you combine them together, how do they affect each other as a whole? You know, does the elongation of AB then cause a compression in BC, and then what does that do for the whole rod ABC? And in part B here, they even ask us that, what is the deflection at B for the system as a whole? So we need to think of it individually and as a system as a whole when we're solving this out. So the same as we've done in our previous problem here, what we want to do is take all that information now from our problem statement, as well as from the initial given diagram, and create our setup page. Now on the setup page, again, we're going to have a couple of main components of this. You're going to have your labeling here of exactly what problem it is. This is for course ME14. This is problem number 219. Here's a brief description of what I'm dealing with. This is an aluminum rod in my problem. And again, if this is for assignment you're turning in, you'd have your name up here and the due date and what assignment number it was right there. You'd write in all that information on the top of your setup page there. And then once you have all that information in, the next thing that we're going to want to do is break it down into what is given, what are they asking me to find, are there any assumptions potentially, and draw out our diagram here, our initial diagram, a simplified version of our given diagram there that we can reference back to. Now, the thing I want to relate this to is your actual grading rubric for how your homework and exam problems are going to be graded. So we saw this was a 10-point scale, where 2 points of this initially are just from your setup. Did you set this up correctly? So just setting up this page here. And my thought process behind this is, let's just say you're stuck. You got a problem in front of you and you're just drawing a blank. You don't know where to start. And that happens to everybody at one point or another. For some reason, you're just like, wow, I can't even think of where to start with this problem. Well, my idea behind this is if you get to that point and you're feeling stuck with those problems, if you do this process, it's going to jog some things in your memory. Like, I've seen this before, or I know that with all these givens and what they're asking me to solve for, I've seen a governing equation that's going to relate these together that I can use. I know that I saw that in an earlier lecture or back in a different section of my textbook, and I can go from there. So I'm going to award 2 points just for you guys writing this setup all down, writing down these are my givens from the problem statement. This is what they're asking me to solve for. Here's my diagram here. Here's everything right there. So that's 2 points. The next 2 points are going to be for is it neat and organized? So did you take the time and do this out so that the grader can actually read through this, decipher what your thought process was, understand what you're doing there? So there's already 4 out of 10 points. You got 40% of the problem just for writing all this down, getting the formatting correct, and doing it in an organized manner. Now the next 6 points are going to be going as we move on with this problem here, where the bulk of it, 4 points, is going to be from choosing that governing equation. So that's what we want to do is with this information here, from all of our givens and all of our finds, figure out what is our governing equation, what is our method for solving this, what is our approach to solve this problem. And that's your 4 points there. And the last 2 points are just going to be, did you get the right answer? So I'm not as concerned, did you drop a negative? Did you put the wrong value in by accident? Is there a carry through error? Now, if you've got this neat and organized, we can easily tell, the grader can easily tell that, yeah, that was just a carry through error, no big deal. You're not going to lose too many points. So this is why I use that 10-point grading system here. And this is why I really want to stress and encourage you guys to create this setup page. And this is going to become more and more important for more complicated problems and some of these more advanced courses you're going to take as you move on within mechanical engineering. So now that that's said, let's go back to our problem here that we're working on. And we say, okay, what information from that given problem statement and given diagram can I write down here? Well, I have, again, 4 different things here. My variable name, my value, my units, and how it relates to my physical problem here. So I have the diameter of rod AB, which you can see over my diagram. That's the top part. Rod AB right there is going to be 20 in units of millimeters. I'm going to convert this to meters, and I'm going to do it right here so I can reference back to this, 0.02 meters. Now I can say, okay, well, what's my diameter for rod BC, the lower portion right here? Well, this diameter is given to me as 60 millimeters or 0.06 meters, and this is our diameter of rod BC. So I have all 4 of those things, variable name, units, value, and how it relates to my problem. Then I can say, well, I also have length associated with this that I can see over here in my given diagram. So I have the length of AB is 0.4 meters, which is given in meters, which is great. Length of rod AB. LBC, which is 0.5 meters, the length of rod BC. So I have it written in my diagram, but I also have it here under my given so I can quickly reference back to this as I'm going through into my governing equations and plug these values in. So from there, I also say, well, I have my P, my load up here at point A that's given to me here as 4 kilonewtons, but I know I want to get rid of the kilonewtons and leave it in newtons right there, so I have 4 times 10 to the third newtons in tension is what this is. My P is my tension. Last thing they give us was our modulus of elasticity. They told us the whole thing, no matter if we're on AB or BC, it's aluminum. Now, this is not always going to be the case. It might tell you the base is made of steel, the top is made of aluminum, maybe they're different types of steel, maybe one's a thermoplastic, so it can change there. In this case here, it's a simplified version, and our modulus of elasticity is the same, regardless of which rod we're dealing with here. 70 gigapascals, I'm going to convert to pascals right here so that we're in newtons and meters, and this is going to be 70 times 10 to the 9th pascals. So now I have all the given information. I have my initial diagram, I have the problem statement there. The last part of this setup page I want to create is what they asked me to solve for. So there was 2 things that they asked me to solve for in this problem. In part A, they asked me to find the value of Q. We can reference back. There's our Q value right there, acting down now the opposite direction of P at point B, so that the deflection at A is 0. So let's think about this for a minute. We want this deflection at A to be 0. So for that to be 0, if we've already kind of thought about this and pulled this here and we're elongating AB, if we don't want point A to move, what needs to happen to BC? Well, BC is going to have to compress if AB is going to lengthen and point A doesn't move at all. So in that case there, if we say the deflection at BC minus the deflection at AB is equal to 0, then therefore the deflection at BC must be equal to the deflection of AB in order for point A to not move. So that's something we really do need to think about within the problem. I'll get into a little bit more details of this as we start our solution there. The second part, part B, they want us to solve for the deflection at point B now. So we're going to show in part A that this doesn't move and find the value of Q such that point A doesn't move. So if point A doesn't move, then we're going to see that this is going to go into compression here in order for that not to move. So how much does this go into compression by? What is our deflection of point B? So next, now that we've taken the time, read through the problem, looked at our initial different diagram, thought about how this rod is going to move, and individual components are going to move relative to each other in this, the next step is to begin our solution. So as we begin our solution to these problems, we go back, we reference that setup page there. Here's the information that's given to me. Here's what they want me to solve for. So what is my governing equation? What can I do? And the other thing we want to do is solve this individual part separately. So for part A of our solution here, what they asked us to solve for is the value of Q. So we want to find the value of Q right here for this problem here. So first thing we need to think about is how do we get to that point? How do we get that Q there? Well, we think about the first problem we went through and how we went from area to diameter. Well, now they give us diameter. Maybe we need to back out into area there and keep going through that same process there. So we start here and we say, okay, let's find the area AB. So we find our area for AB. So again, we're looking at AB and BC separately. So I'm just dealing with AB right now. First, AB for my area here. I've already went through and how I derived this here in the previous problem from from area is equal to pi r squared. So we're doing this for diameter here now. So we're just using diameter rather than radius. So our area at AB, and I label my indices. Indices become important. It lets us know what part of the problem we're dealing with, especially with more complicated ones that have individual components and a lot more components associated with them. Make sure you have a good labeling system and have these indices correct, something that makes sense. And label them too. This is AB, and I'm telling you this is area AB. So I'm saying exactly what it is, and I'm showing what the variable is. So this is equal to pi over 4 times my d, AB. Again, I label this here. This is a diameter of AB, not just diameter. That can be confusing really quickly. This is diameter for AB, and that's what I'm looking for here. So I back this out, solve this for diameter of AB, or for area of AB by plugging in my known values here, where my diameter of AB is 0.2 meters. I plug that in over here, so I end up with my area of AB is equal to pi over 4 times 0.02 meters squared. Plug this in, solve it. What I end up with, my area of AB is equal to 314.16 times 10 to the negative 6, so that I can keep my units in meters. This is meters squared right here. So now I want to do the same thing for my lower body of our system here, which is member BC. So I do that there. I use the same equation right here. Now for my area of BC, you can note my indices there. The area of BC in this here is equal to pi over 4 times 0.06, which is my diameter that's given to me in meters of member BC squared right there. Plug that in and solve it. I can find now that my area for member BC is equal to 2.8274 times 10 to the negative third, again in units of meters squared. So now I have my area, my cross-sectional area for the top member AB and the bottom member BC. So where do we go from there? Well, let's take a look at the top one. The reason I want to start with member AB is because we have information related to that P that's associated there. Q, we don't have that information yet, so let's go through and find our governing equation for the elongation. We've already kind of proven to ourselves that if we pull down with Q and we pull up with P right there, we're going to see that we're going to have a elongation of this member right here. So we do that there. We can say, okay, we're pulling up with P down here, up here at the top right here. We're going to have an elongation in member AB. Well, our deflection in AB, so now you can note my indices here, is going to relate back to this equation 2.9 on page 70 of our textbook right here. This is our general governing equation. So I'm putting in the indices related specifically to this problem for member AB. Load, our tension force here, P, times the length of that member right there, AB, divided by our modulus of elasticity times our area of AB there. So let's just say on the previous slide we didn't know we had to solve for area off first. We would have went to this equation, got to this equation, realized, I need my area, and gone back and solved for that separately. So the more of these problems you do, the more you'll know I'm going to need the area in order to use this equation 2.9, so therefore I'm going to solve for it now. But there's nothing wrong with saying, hey, this is my governing equation right here, and separately I'm going to solve for my area term so that I can plug it in. So with that information known there, we have all of our values that we were given here. Our load is given to us right here, so we can plug this value in for our load, 4 times 10 to the third newtons. Our length for member AB is 0.4 meters, and our modulus of elasticity is given to us as 70 times 10 to the 9th pascals. And we've just solved for this A sub AB on our previous slide here. 314.16 times 10 to the negative 6 in units of meters squared. So now we can take all those values, plug them back into this governing equation up here. And when we do that, we can solve for our delta AB. We can see our load right here, 4 times 10 to the third in newtons. We can see our length right here, 0.4 meters. We have our modulus of elasticity here, 70 times 10 to the 9th pascals, and our area of 314.16 times 10 to the negative 6 units of meters squared. And what I've done here, I can do out my unit analysis. The first thing I want to do is take a look at pascals. I want to get pascals in terms of meters and newtons and meters right now first. So we say, okay, a newton is a kilogram meter per second squared. So I can get rid of my newtons right here and then convert to meters per second squared. And I can say that a pascal is a newton per meter squared. So I can get rid of newtons here by plugging in this value for newtons here into this. And I can say that pascal is a kilogram divided by meters times seconds squared right there. So now far I've eliminated newtons and I've eliminated pascals. So now everything in terms of kilograms, meters, and seconds in this problem right here. So that makes my life easier when I start doing my unit analysis out. So I redo these where I replace newtons by my kilogram meters per second squared. And that's this right here. And I replace my pascals by kilograms per meter times second squared from this right here. Plug those two values in. My length was in meters, and my area was in meters squared right there. So now I can go through and say, okay, meters here cancels with meters here, kilograms cancels with kilograms, second squared cancels with second squared. And then what I'm left with here is simply 1 over meters, which deflection should be in meters, which it is. So I know this is a little bit extra step along the way to do these all out with all this unit analysis over here on the side, but it helps a lot, and it's a great way to double check your work. Did I plug in correctly? Did I use the right units for my modulus of elasticity, for my loads? Did I plug this in right with the right units for area there? And if it doesn't check out, it's a good alert for you, a red flag that, hey, something was wrong. I didn't do my unit analysis right. I didn't have my conversions right. I plugged in a wrong value. Do that out with all these problems. It's going to save you a lot of time and really a great way to double check your work. So when we do that out, we can find our deflection at AB, and this is equal to 72.758 times 10 to the negative 6 in units of meters. Now, again, we're breaking this into individual components, individual sections that we're solving. We went for AB, now we'll go for BC. And what we can see here is in BC, we have this load right here acting at point B. And this point B is of interest to us in part B of the problem here because we want to see how does that move there. So the load we have acting on this is not just Q, it's Q minus P. And the negative sign has to do with the directionality. So P was pulling up in the problem and Q was coming down in the problem. So therefore this is Q minus P acting at the top of member BC here as it sits on a rigid surface down below. So now when we go back to equation 2.9 of our textbook, when we plug in for our load value here, our load that we're interested in is this combined load from our P and our Q right here. So we plug in Q minus P right here for that portion of equation 2.9. Now that is multiplied by our length, or length of member BC, divided now by our modulus of elasticity. And recall, it's the same modulus, it's the same material for all, but for E doesn't change, whether we're dealing with AB or BC. And our area for BC there. So now we want to plug in our knowns. We can go back to our initial setup page and say, okay, my length of BC, I know was given to me as 0.5 meters. My modulus of elasticity for both top and bottom section were 70 times 10 to the 9th pascals. And my area for BC, I can calculate, and I've already done that based upon my diameter there, and this is going to be 2.8274 times 10 to the negative third in units of meters squared. So from that there, I can plug these all in to my governing equation 2.9. I plug them in here and I can say, okay, my delta BC, again, units right here, pay attention to these indices right here, is equal to Q minus P times 0.5 meters, all divided by my modulus of elasticity here, 70 times 10 to the 9th pascals, times over here, my area for member BC now is 2.8274 times 10 to the negative third in units of meters squared. I can do this out, do up my math. What I end up saying here is delta BC is equal to 2.5264 times 10 to the negative 9 times Q minus P. And the next thing we want to solve for is our Q. So what we want to think about now is a part of the problem that tells us that the deflection at A is 0. We were solving for Q if the deflection at point A at the top here is 0. So the compression of BC at the bottom must be equal to the elongation of member AB at the top. So however much we're stretching AB, this needs to be down here in compression, down right there, so that there is no deflection at A. In order for this, in terms of our variables, this is saying that DBC, our deflection at BC, is equal to our deflection at AB there. So that's going to help us solve a portion of this relationship here in order to get our deflection at A to be 0. So what do we know about the deflection at AB? Well, we've already solved for a numeric value for our deflection at AB. So our deflection at AB is equal to 72.756 times 10 to the negative 6 meters there. And we have now down here this relationship for DBC relative to our Q and our P right there. So now we can set these two relationships equal to each other, because if DBC is equal to DAB, then this relationship on the right-hand side of BC is equal to this value right here. So we can do that there. If we've written this down again just in the top of the page, we set these equal to each other. When we do that, we end up with this relationship right here. So 2.5263 times 10 to the negative 9 times this Q minus P is equal to 72.756 times 10 to the negative 6. We can solve this for Q now, and we can say, okay, solve for Q minus P now, and we say that Q minus P, divide this over here, just leave this by itself. We do out our math here. Is 28.8 times 10 to the third newtons. Is Q minus P? Well, give us our value for P in the problem statement. So now we can plug that in for P. Our only unknown here is one equation, one unknown at this point. Plug that in. Q minus our value for P, which is 4 times 10 to the third newtons, is equal to 28.8 times 10 to the positive third newtons. So what we have here now is Q is equal to, we can rearrange this a little bit and solve it for Q, 4 times 10 to the third newtons plus my 28.8 times 10 to the 3 newtons right there. Both the units are newtons right there. We end up solving this together. What we find out is Q is equal to 32.8 kilonewtons. So that's what we asked to solve for. We're asked to solve for Q right there, so the A does not move, and that's how we do it with this relationship here and this Q minus P relationship, and the fact that we can set those two deflections equal to each other. So that's solved for part A. Now we're moving on to part B, where they asked us now, okay, we know this Q, so the A doesn't move. Well, then what's going to happen to point B? How does that move? Where does that go? What direction is it moving in? What is the value there? Well, it's going to deflect going down right here. It's going to compression. So if A and B is in tension and elongates, BC is going to be in compression right there. We can still use the same governing equation right here. So we know that the deflection of BC is equal to that Q minus P times the length of BC all over E times the area of BC there. Now we can plug in. We now have value for Q. We now have a value for P right there. We can plug both of those right in units of newtons right there. We know that the length of BC is given to us as 0.5 meters. We know the modular elasticity doesn't change. The material property is the same for that, 70 times 10 to the 9th. And our area for BC, we already calculated as 2.8274 times 10 to the negative third in meters squared. So you can do our unit analysis out like we did before and double check this comes out in meters, which it does. So we end up with the deflection at point BC is equal to 72.756 times 10 to the negative 6 meters. So to think about this here, if DAB is equal to DBC, which we said it was, then we know that this is moving to elongate. This is moving in compression right there. So our deflection in B is going to be equal to that distance right there. So our deflection in B, as we've just shown there, is going to be equal to 0.072 if we convert back to millimeters in the beginning right here rather than meters. And it's be going, the direction we're moving down is right here into compression.